Thank you. First, thank you to the organizers for inviting me to present my work here. I'm going to work about I'm going to work about a deformation model to incorporate deformation prior in shape analysis, and this is joint work with Stanley Doleman, Alain Trouvé, and Olivier Verdier. So first, small reminder of how we can use deformations for shape analysis. So the idea that we all use is that in order to compare two shapes, so here two skull shapes, in order to study the similarities and the difference between these two shapes, we study the deformations that enable to transform the first shape into the second one. And when the two shapes have the same topology, we have no loss of matter, it's reasonable to construct these deformations as diffeomorphisms. And a suitable way to build diffeomorphisms is to build them as flow of trajectories of vector field, so satisfying this differential equation. And we will call a large deformation the final value of such a flow. So if we want to use this kind of deformations, parametrized by trajectories of vector fields here, in order to perform registration, it amounts to this kind of minimization problem. So we set a space of vector field V, and we consider a subset of trajectories of L2 trajectories on this space, so W. To each of these trajectories, so time-varying vector field, we can associate a cost, an energy. And thanks to that, we can associate this energy, which is the cost gives a regularity. And here's the data attachment term that measures how well the first shape is deformed close to the second shape. A very well-known case of this is the LDDMM framework, where the set of trajectories that we consider is all the trajectories that are square integral, can be square integrated, and the cost is given by the L2 norm in this space. This framework is, as you know, very suitable for many reasons. In particular, we can prove the existence of minimizing trajectories. They can be parametrized by an initial variable called momentum. And besides, the actions of vector fields on shapes enable to equip the shape space with a metric, structure of varifold with a metric, such that the distance between two shapes is equal to the minimum of the energy required to transport the first shape into the second one. And this structure of manifold enables, for instance, to perform statistics on the shape spaces. So this gives very good results, but as here we allow all trajectories, almost, in the space of vector field, sometimes the result that we obtain is not the result that is satisfying from an intuitive point of view. Like here, for instance, if you want to match this image into this one, so this is shape Logan, which is a common phantom used in tomography. Typically, the trajectories with LDDMM that you would obtain are this kind of thing. So if you look, this structure here kind of shrink. So the data attachment term at the end, if you take L2, it's not so big, of course. So from what we wanted, it is working. But from an intuitive point of view, this is not what we wanted. Of course, what we would like to see is a rotation of this structure rotating in order to become this one. In order to enforce this kind of behavior to happen, the idea is to incorporate a structure in the space of trajectories of vector fields that we'll consider. This will be in particular very important when the target here, so the target shape, is not very well known, so if it is very noisy, or if we have indirect observation of it, like what Klaas Modin talked about yesterday, and it was developed in an article by Shongshen and Ozan Öktem. So for instance, if instead of knowing your target shape, you know its rate transform for only several angles. Various models studied the ways to incorporate structures in large deformations, but to our knowledge, there are no models that enabled to both incorporate easily a structure in the deformation model, for example, enforcing to have a rotation somewhere, a scaling somewhere, and at the same time unable to have a strong mathematical framework For instance, linking the energy with a structure of manifold on the shape space and a distance on this shape space. So this is what we intended to do with a deformation model based on a structure that we called deformation modules. Deformation modules are structures capable of generating vector fields that are of a particular and chosen type. So a deformation module is given by 5 elements, and I will explain how they interact thanks to a diagram like this. So as I said, deformation modules can generate vector fields, and these vector fields will be parametrized by 2 components. The first component is what we call a geometrical descriptor. The geometrical descriptor will code for the geometry, for example, the location of the generated vector field. I will denote by O the spaces of geometrical descriptors in general, and by Q the elements of this space. We require that the space of geometrical descriptor is a shape space in the sense that it can be acted on by diffeomorphisms, so it can be transported by diffeomorphisms. The second variable that will parameterize our vector fields is a control variable in the sense of control theory. The control will code for how and how much we want to use the generated vector field. The space of control is the vector space, and I will denote by H this control space, and small h the elements of this space. Then, field generator is a function that goes from the product space of geometrical descriptor and control to the space of vector fields of a certain regularity, L here, and that tends to 0 at infinity. So the field generator takes in input one geometrical descriptor, one control, and gives the vector field parameterized by this geometrical descriptor and this control. So by choosing the field generator, we will choose the vector fields that we will allow in our deformation model. So thanks to this field generator, we can incorporate a prior on the type of vector fields that we want to generate. As I said, the space of geometrical descriptor can be transported by diffeomorphisms, and by differentiating this action at the identity, we obtain the infinitesimal action of vector fields on geometrical descriptors. So the infinitesimal action says how a vector field can infinitesimally displace the geometrical parametrization of our vector field. Note that vector field. Note that the infinitesimal action takes here any regular enough vector field input, not only these that are generated by the field generator. So this is an important feature. And last, we have a cost here. We have to define a cost that says how much it costs to use a particular value of geometrical descriptor and control. Note here that the cost is applied to the parametrization, so on geometrical descriptor and control, not on the generated vector field. So if we have 2 parametrization of the same vector fields, we can differentiate them thanks to the cost. So we can associate a lower cost to a parametrization that is more satisfying intuitively, and so we'll be able to favor it when we minimize the cost. So I will now give a very simple example of deformation modules, the one that generates vector fields that are always local rotation, localized by a Gaussian kernel that is of fixed size sigma. So this is one example of vector fields that can be generated by this deformation module. And here's the diagram representing this deformation module. A local rotation will be parameterized, so it's an infinitesimal rotation, and it's parameterized by 2 variables. First, its center, here, and second, a scalar that says how much you want to rotate. The center codes for the geometry, the location of the generated vector field, and so it will correspond to the geometrical descriptor. So our space of geometrical descriptors will be the set of all points we are in dimension 2, so it's R2. The scalar will say how much you want to rotate, so it's the control. It says how much you want to use your infinitesimal rotation, so the space of controls is R. Then the field generator associates to a center, a geometrical descriptor, and a scalar. This scalar times the local rotation centered at the point Q, so the geometrical descriptor. For the cost, I take H2, this is a choice, and I decide that the way vector fields transport geometrical descriptor, so the way they transport the centers of rotations, is by just apply them to the center. So we just apply vector fields to the geometrical descriptor. This is, once again, a choice. So this is an example of deformation module that will generate vector fields that are always local rotation. On the same idea, we can define deformations modules that generate vector fields that are always local scalings, local shearings, or local translation. Any kind of deformation you can imagine like this. But of course, in practice, we do not want to perform registration with just one scaling on one rotation. We want to have one rotation here, one translation with a bigger scale, one smaller rotation somewhere. So in order to do so, we'll have to combine different deformation modules. So let me introduce how we can combine two deformation modules. Let's assume we have two deformation modules here. For instance, one generating a local rotation at a certain scale and one generating a local scaling at a certain scale. The way, if we want to combine them, it means that we want to combine the generated vector fields. So we want our new deformation module to generate vector fields that are combination of one rotation and one scaling. What does it mean? It means that we want to sum. So we want to have, for each geometrical descriptor and control, the generated vector field being a sum of one local scaling and one local rotation. So this is exactly how we'll define the composition of two deformation modules, the combination of two deformation modules. So here's the diagram. It's very intuitive. The new space of geometrical descriptors is the product of the two previous spaces. The new space of control is the product of the two spaces. Then the field generator takes in input one geometrical descriptor that has two components, one control that has two components, and returns the sum of the two vector fields that would have been generated by our two deformation module here. The infinitesimal action takes in input one vector field and will apply it to geometrical descriptors that have two components. It will apply it to the first component thanks to the first infinitesimal action, and to the second component thanks to the second infinitesimal action given by the second deformation module. And we take the cost, the sum of the cost. So this is an easy way to combine automatically two deformation modules. We can combine as many as we want. And thanks to this, we can build deformation modules as complex as we want, which means that we can define priors on vector fields as complex as we want. Because here now, our new prior is that our vector fields are sum of one rotation and one scaling. So now that we can build complex priors on the level of vector fields, we have to take this prior to the level of large deformations. In order to do so, we first have to restrict ourselves to a certain type of deformation modules. These that will satisfy what we call the uniform embedding condition, which sets that there exists a Hilbert space of vector field V and a constant C, such that for each geometrical descriptor Q and each control H, the vector field that is generated belongs to the space V, and its norm satisfies this inequality. This inequality means that if you can control the cost, then you can control the norm of the generated vector field in a fixed space of vector fields. So that will enable to consider trajectories and integration. In the following, I will always assume that the deformation modules satisfy this uniform embedding condition, and the one that I've presented previously, they satisfy. And one very interesting feature is that if we combine two deformation modules that satisfy this condition, then the combination of these two deformation modules will satisfy also this condition. So it's an easy way to build complex deformation modules that satisfy DVC. It's just to combine simple deformation modules that satisfy this condition. So now we assume that we have one deformation module as complex as we want thanks to combination and satisfying the UC condition. As I said, we want to build large deformations. They are parametrized by trajectories of vector fields. Here we want vector fields that are given thanks to the field generator. So they will be parametrized by trajectories of geometrical descriptors and controls. So we have to decide what are the trajectories of geometrical descriptor and controls that we'll consider. We'll consider what we call finite energy control paths, which are trajectories of geometrical descriptor and controls such that at each time the speed of the geometrical descriptor is equal to the application on itself thanks to the infinitesimal action of the vector field which is generated by this geometrical descriptor at this time and the control at the same time thanks to the field generator. So what does it mean? It means that we consider a trajectory of geometrical descriptor and controls. Then, thanks to the field generator, we obtain a trajectory of vector field here. And what we impose is that, in fact, we have a feedback loop. So the vector field at each time gives, by its application on the geometrical descriptor at this time, the speed of the geometrical descriptor. So we will only consider trajectories such that this feedback loop is indeed effective. We'll also assume that the energy, defined as the integral of the cost, is finite. Then we can show that the trajectory of vector field here can be integrated, its flow exists, and this is what we'll call a modular large deformation. Besides, we can show that this modular large deformation is parametrized by the initial value of the geometrical descriptor and a L2 trajectory of control. Indeed, then we can integrate this differential equation and we obtain, in fact, a finite energy control path. So in the following, I will parameterize the modular large deformation by an initial geometrical descriptor and a trajectory of control. So now, if we want to use these modular large deformations in order to perform registration, we obtain this minimizing problem. So we want to minimize this functional that is defined on a set of geometrical descriptors and L2 trajectories of controls. To each couple like that, we can associate the trajectory of geometrical descriptors starting at A and satisfying the same differential equation as previously. We obtain a trajectory Q of geometrical descriptor. We can associate the energy here and the data attachment term, which tells how well the source shape I0 here is transported close to the target shape I1 thanks to the modular large deformation parameterized by this geometrical descriptor and this trajectory of control. We could prove that there is minimizing trajectories of control exist and they are parameterized by an initial quantity called the momentum. We could also show that these vector fields allow to equip the shape space with a manifold structure with a metric such that the distance between two elements of our shape space is equal to the minimization of the energy among passes bringing the first shape into the second one, and that we hope that it will lead to being able to perform statistics on our manifold of shapes. Let me show you a simple example of modular registration here. So we assume that we want to register the pink rabbit head into the black one, and we assume that we have a prior on the deformations that are allowed here. We assume that the way this shape, this purple pink shape, can be transformed is by a rigid transformation, so translation and rotation, and changes in the size of ears here. What we also assume is that we know how to transform this prior information into a module information. So I assume the way I will do it is that I will build the deformation module that generates vector fields that are sum of 4 vector fields. The first one is a translation, a rigid translation. The second one is a rigid rotation. And the two last one are small local translations localized around top of the ears with directions aligned with the size of the ears. So now, in order to perform the registration, I have to estimate initial geometrical descriptors and trajectories of control, allowing to bring the pink shape into the black one. So here are the estimated initial geometrical descriptor, center of translation and rotation, I mean, for visualization purpose. And here, for the two local translations, here are the two centers, and the vectors are as we want them to stay aligned with the size of the ears. It means that if the ears are rotated, the directions of the vector needs to be rotated also. So it means that these vectors have to evolve with the geometry. So they need to fill the geometry, and so they are part of the geometrical descriptor. That's why we take the vector here of the translation partly into the geometrical descriptor component and not only the control. For these two translations, the control will be scalars, so that the translation will be this scalar times the pink vector here. And for the rotation, it's a scalar as previously. And for the rigid translation, the control, the way we want to say where we want to go, is a vector at each time. So here the trajectory, in red are the controls. And so you can see that the combination of these 4 vector fields at each time allow to transport the pink shape into the black one. What's interesting is that the vectors of the local translations that align the size of the ears stay aligned. They stay aligned with the ears because as the directions are part of the geometrical descriptor, they feel the way the diffeomorphism act, the global diffeomorphism act, and in particular, they feel how the rotation rotates the whole ambient space. So they will stay aligned with, naturally, thanks to the infinitesimal action, they will stay aligned with the size of the ears. So this is, this example works well, but it is a quite easy example in the sense that we assume that we know how to transform our first prior information into a module information. I assume, for instance, that I knew the localizing function for the 2 local translations here. And of course, in practice, it's not always the case. If I go back to this example, and I want to apply the same idea. I say, okay, intuitively, we know that we want to have a rotation occurring around here. So if I use the same idea, previously I was using scalar Gaussian kernels to localize my functions. So I can say, okay, let's build a deformation module. We generate vector fields that are always local rotations, localized by a Gaussian function, and I assume I take the scale, roughly the size here, half of the size here. And if you see here is the type of trajectories that I can obtain. So this thing is rotate, but if I go back and if you look here, you see that, I don't know if you see that this structure is also affected by the rotation. So this means probably that the kernel here is too big because, okay, it transports the structure that we want to rotate, but it also affects other structure. And we don't want this because here in the target, this structure is similar to the source shape. So maybe we say, okay, we can maybe reduce the size of the kernel. So here is when I say I take a size for the kernel that is 75% of the first one, and we can see that it doesn't work. It doesn't bring all the structure. So it will not give satisfying results. So we say, okay, this is probably because I took an isotropic kernel. Maybe if I take an anisotropic one, and maybe an anisotropic one, which is flat at the beginning and then decreases fast. But when the structure here rotates, I need to have the anisotropy to rotate also. So it starts to be quite hard. Of course, I could be able to design a good localizing function satisfying all the requirements that I need, because this is quite an easy example. So if we want to take another direction, we need to be able to define an appropriate deformation module given a prior that is not given as a deformation module. So let's assume that we have the priors that we really have, which means we know here that we would like this structure to rotate. So the prior that we have is that we know a displacement field that we would allow only for the source shape. So here we know that we want have the local displacement that we want to have here is a rotation localized maybe in a rectangle shape, something like that. We know only this. How can we define a deformation module using this? First, we have to transform this knowledge of displacement into a knowledge of vector field in a suitable V, space of vector field. So we set a space of vector field RKHS. For instance, I can take a very simple one, like scalar Gaussian RKHS, with a very small sigma, twice the size of the pixel, for instance. and I use the projection of this displacement field in this field. Then I have to build what I will call an appropriate deformation module. So I have to define what is an appropriate deformation module. In order to define this appropriate deformation module, we have to say, now that we know a reference vector field, I will call a reference vector field here the projection of our initial displacement field. What are the other vector fields that I want to be able to generate? Intuitively, given what we have here, if the little structure here is rotated, we want the vector field to be also rotated. So we want to be able to generate rotations of this vector field. If this structure is translated, we want the vector field to be also translated. So intuitively, here, that's a choice. We would like to be able to generate rigid transformation of our initial reference vector field. In a more general setting, if we set a group of geometric transformation G, so in our special case, rigid transformation, we want to be able to generate the orbit of the reference vector field under the action of G. Of course, we have to define this action. It's not so hard. But we also have to ensure that we stay in V, or at least in another suitable space of vector fields. But in fact, we don't only want to generate this orbit, because if I'm able to rotate in a sense, I want to be able to rotate in the other sense. That's logical. So it means having minus this. And I want to be able to rotate twice as hard or half as hard. So what I want to be able to generate is the union of all the scalars times the orbits, like that. So, okay, now we say, okay, that's the vector fields that I want to be able to generate thanks to my deformation module. How do I parametrize these vector fields? We have a natural parametrization given by this. So the parametrization will be an element of our group and a scalar. The element of the group says how the vector field is geometrically transformed. So intuitively, this will correspond to the geometrical descriptor, while the scalar says how much you want to use this vector field. So intuitively, it will correspond to the control. So now if I go back to my example, where G is the set of rigid transformation, the action of rigid transformation, so if you have this parametrization on the vector field, it's this. It comes from the differentiation of the push forward action on diffeomorphisms. And so we know, thanks to this, what are the vector fields that we want to be able to generate. How we can parametrize it? We could parametrize it by really parameterization of rigid transformation, but we need to define how we can act on theta and how we can act on C, and it's not really the most suitable way. So another way would be to say, okay, how can I know a rigid transformation? I can know it by the action on 2 points. If I know the action on 2 points, I can go back and know my rigid transformation. So let's say that we have 2 points, N, A, B. What we want to have is that if this is the vector field generated thanks to A and B, if I move A and B in a rigid way, I want my vector field to fill the same deformation. So if A and B become A prime, B prime, we want the vector field to fill the same thing like this. So this is how we will use this. So we say that this is the transformation transforming AB into A prime, B prime. In fact, it's not exact. This is if A prime, B prime is really a rigid deformation of AB. But if it's not the case, this will transform the mean points into the mean points and the orientation into the orientation. So if they are, if the distance is multiplied by 2, I will still use this, this transformation. So what we want, as I said, is that if VAB is generated by A and B, then if we displace, if we have A prime, B prime, we want the new vector field generated by A prime, B prime to be the rigid transformation transforming AB into A prime, B prime applied to V, thanks to this action here. So we want the vector field to be rotated the same as the line AB, and we want the vector field to be shifted the same way AB are shifted in order to go to A prime, B prime. And besides, if we go back, we want always our vector field to be a rigid transformation of our reference vector field. So if we put that together, we can show that in fact V A prime B prime will be written like this, but in fact it will be a rigid transformation of the reference given, and the rigid, we have the expression, but pointless to write it here, but it's parameterized by not only two elements, so A prime, B prime, but also two other fixed elements, C0 and theta 0. And these elements are such that if I change A prime and B prime into something else, but I keep C0 and theta 0, then the new vector field will satisfy this equation. I will call this zeta, so this will define the field generator, and Q, the geometrical descriptor, it will be these four elements, not only A and B. So I will, it's Z0, zeta 0, A and B, or A prime, B prime. So now we can define our deformation module. The space of deformation module, as I said, so C0 is a point and theta 0 is an angle, initial angle. So the space of geometrical descriptor will be this. We have a point, an angle, and 2 points. The space of control is a scalar space, so R. The way we can generate a vector field is by multiplying the control, the scalar control, by the vector fields that I gave here. And the infinitesimal action is the way a vector field can transform a geometrical descriptor. And as I say, what we want is that when we displace A and B, the new vector field is a rigid transformation of the previous one given the ways A and B were transformed. So the infinitesimal action will not displace the first two components, it will displace only the second one. So this is infinitesimal action. And the cost, I just take the square of the cost. So this is a deformation module that is automatically defined given two things. First, the reference vector field, and second, the group action, so here, the rigid action. Once I have decided that, I automatically can define these deformation modules, and this deformation module will satisfy the uniform embedding condition. And here, I will show the registration, modular registration given this. Here's the trajectory that I obtain. I plot here the points corresponding to A and B, not C and theta, because they don't move. And in fact, the initial point C and theta and the initial angle, they just correspond to initial registration, initial rigid registration for the initial vector field. Sorry. Well, so this is the trajectory that I obtain. Here is the deformation grid. So we can see that thanks to this, we could automatically, just given the displacement field, the initial displacement field, which was roughly defined, we estimated the support of our rotation. This support is following the evolution of the geometry, and it gives, in fact, what we wanted, and everything. This is automatical. As I said at the beginning, this can be very useful if we have very noisy data. Like here, if I perform the registration of this source shape into this target, so the target is super noisy here, and if I assume, once again, I only assume that I have the displacement field that I gave at the beginning, and I perform the registration, and I obtain something, I mean, almost perfect. It's not totally rotated, but given the data, it's quite good. And of course, thanks to this, we now have a parameter parametrizing the rotation. So if now I want to study how far the rotation has been, I can study this parameter. This can also be used for indirect matching, as Klaus was showing. So here we have that. And instead of knowing the target, I know it's retransformed only for two angles. Here is what I obtain, the trajectory on the left. So once again, it's not totally, maybe it's an optimization problem, I'm not sure here. And here are the data. So I only have the retransform for two angles. So that's the data for these two angles. I don't know if you can see in green, it's so the difference is only very localized. That's normal because it's only here. In green, it's for the initial template. And in black, it's the noisy data. The blue is the ground truth, so this. And in red is the result. So you can see here that the result is not totally fitting, but it became to be the good one, close to the good one. So now, all the red transforms and dealing the distance in images, it's implemented. I used implementation of ODL, which is a library developed in KTH by Jonas Adler. So last example, if you have a more complicated data. So here, we have this structure that is rotated, but we have also other displacements. So now I want to do the same thing. Once again, I need to have a prior. So I assume that the prior is that this is the initial displacement field that we allow. Of course, here it makes no sense to say that what we want are rigid transformation of this displacement field. It would be pointless. I mean, there is no reason why we would have that. So this prior would not be relevant here. What we assume, though, and that's a first step in our research, it should be, is that we know how to decompose this displacement field into components that are logically can be acted on by rigid transformation. So we know that this displacement field can be decomposed like this. Once we know that, we automatically can compute the deformation modules corresponding to each component as previously, and we can combine them, and we can perform the registration just as previously, and we obtain a good matching. So here the only problem is that we assume that we know the decomposition of the first displacement field, and what we are working on now is how to estimate it given several observations. So it means that each component will have rigid rotation, and maybe it goes to what Stefan Marsland was talking, how to say finding invariance. So we're working on something like that with Olivier Verdier, and how to estimate the component given that you observe some of them that are rigidly rotated. I decided to use mostly rigid transformation, but can be translation, only rotation. The hypothesis here is that if we need something more complicated than a rigid transformation, it means that you have to separate in several components, which means, I think, reasonable. And the next step would be to be able to generate vector fields that change scale. For instance, if you're talking about a contraction like this, it doesn't make sense to have the scale of the vector field to be the same. So the way the geometry is felt by the vector field should incorporate a change of scale, but this changes the kernel, so it's more complicated. So I'm working on this too. And last, instead of working on displacement field, which makes sense if you have, sometimes it makes sense, but sometimes it doesn't, and would like to be able to estimate this displacement field from directly a trajectory of image, which would give us several observations, but as we wouldn't have point of correspondence, it makes it once again harder. So thank you for your attention.
Questions? Yes, class.
When I saw this first bunny example you had, I was thinking about the rigid body. Because in the rigid body you have two ways to describe it, either using left translation or right translation. If you use left translation, it corresponds to a body frame, it's sort of following the rigid body, and if you use right translation, it's like a spatial coordinate system that you fix. In LDDMM, normally you use right translation, right? So that's like a fixed background frame. But here, it seems like it would be more natural to reconstruct the diffeo by left reconstruction instead. Because then you would automatically get something that follows, you know, the components in your vector field would sort of follow your flow. You see what I mean?
I'm not really, sorry.
I think it should be the controls act from the left. Okay, so how do your controls act? What's the time dependence of your controls? How do they respond to the diffeo?
Of the control?
Yeah.
You mean the regularity of the control?
So you wanted to have some, going to have two actions, right? So one action is going to be by the diffeomorphisms, and say, and the other action is going to be by a rotation. So how do you get the rotation to keep track of the change of shape?
It's only one action, in fact, because the rotation, what we have is that at each time you have a vector field, and indeed the vector field has several components. One of each is rotation, but then it's a vector field, and you integrate the trajectory of vector field, and the geometry of all the geometrical descriptors follow the whole. Like if we go back to the definition of the composition of deformation module here, I didn't insist on this, but like say that you have one here. If you have one deformation module that generates a rotation, and you have one deformation modulus that generates whatever you want. What we do is that we combine them, and so the way the geometry of the rotation fills the global evolution of the ambient space is thanks to the infinitesimal action. The infinitesimal action applies a vector field to, let's say, the center of the rotation, and the vector fields that are applied are the combination, the sum of all the vector fields. So if you have a rotation and a translation, you will have the vector field that is generated each time is the rotation plus a translation, and the way the center of the rotation, what the center of the rotation will feel is the combination of this local rotation and this translation.
So it seems like a semi-direct product.
Somewhat?
Semi-direct product, right, of these infinitesimal actions.
Yeah. Already, but I don't think it's
The action of the diffeomorphism. On your geometrical descriptor, which is the shape space, on which you can act by diffeomorphism. So this infinitesimal action is just there.
But
So you transport, it can be landmark, it can be landmark with vectors, it can be whatever. So you have this infinitesimal action. And after you have this bit generator, which is creating this mapping, a linear mapping, given the position of your geometrical linear mapping from the control to the vector fields.
I had a similar question. This all makes perfect sense when you have this kind of action. But when you went to the A-B points, now you've got this, they're acting via the composition of all the combined velocity fields. So what stops the points from moving apart and not being any more rigid?
No, I don't assume that the way they deform during the integration is rigid. I don't assume that. That's why I said that the way.
Then,
what I say, that's why I said what I define here.
yeah.
The way what I call like that is if this is a rigid transformation of AB, it will bring A to B and B to B prime. But if not, it will bring the center into the center and the angles into the angle.
You somehow or other project them back to a rigid transformation. I mean, I'm confused. Why are you doing that? Because one would expect the natural action, infinitesimal action of the diffeomorphism. We know what that is on, if you want to have rotation.
Yeah, but if you want to have, like, if you take, for example, the action by differentiating on the center, something
Right.
like that, it's very depend. The idea is that it's very first for the noise it can be a bit annoying, but it's also sometimes it's not what's important. It's not you could decide that. That's just one example of parametrization. You could decide that, but what's here the idea is that you have with this point is that you have you have a direction that is of importance, that the way this direction in really not in infinitesimal sense, but really the way it evolves, it defines the structure. Because here we see that what creates this rotation is the structure with the 3 disks. Okay, so if this point goes far here, as it will feel the same vector deformorphism as the how to say the image, and so it means that all this area in this image has gone here.
Yeah.
So if you have so it doesn't make sense to have only.
But in your framework, when you define this nice framework, you said it was infinitesimal action. So is this
the infinitesimal action here is this one. So.
Yeah, so that's infinite. But then taking from here to the rotation is the complicated rotation. Is not.
No, the rotation. I mean, it's I have a very easy way to from Q, so C0 theta 0 AB, to define a rigid transformation. That's one line, and then I have one other line to say how it acts on my reference vector field.
That's just V of A. So that is acting infinitesimally on A.
Yes. Here it acts on points.
Yeah, so it's just a matter of mapping from V of A of AB to the reference frame. That's complicated.
Yeah.
Okay, okay. All right. Okay, now. Thank you. Now it's clear.
So we can go now.
We can go. No, any other questions?
Yes, let's have coffee.
Okay, let's. Thank you very much.
Thank you.